All right, how fast does this reaction occur? This actually isn't about quickness or whatever. Well, I guess it is. Progression of reaction, kind of think of that as time along the x-axis. But this is an energy diagram, energy along the y-axis. And we talked about this before. You draw the energy associated with reactants, the energy associated with the products. Of course, since there's less energy with the products than there is the reactants, you guys think this is endothermic or exothermic? It is exo, that's right. Energy is released as basically, as it proceeds from reactants to products. Very good. So it's going to be a negative enthalpy change. Very good. And then that little hump, that little energy hump from the reactants, okay, it goes up and then it goes to form products either higher than the reactants or less than the reactants. That hump is the activation energy. So we have actually a few things added on here. We have something called a transition state. So to me, we have two reactants, the N2O and the NO. Actually, can you see at the hump of the energy barrier? That's kind of where you have them kind of getting ready to do something. In this case, think of it as your N2O is going to kick off an oxygen, and it's become part of the NO. It's kind of how the transition state is shown up there. We have a transition state. Something interesting here also, I didn't realize it till just now, or not this semester anyway, but notice that if we were to go back the other direction, of course that would be something, not a reaction in a one-way direction, that's a chemical equilibrium. Notice if you were to go back from products to reactants, it would be endothermic by the same amount, as far as my math can tell, as far as we talk about those enthalpies of reactions. And in that case, the activation energy actually would be from the products, which now are reactants, up to the top of the transition state. So which one has the more activation energy? Going from left to right or from right back to left again? More activation energy.
Maybe left to right?
Here's the activation of the forward. Here's the activation of the energy. From right back to left again, the activation energy is greater. Yeah. That's a little bit of an aside. Now yesterday, or you know what I mean, Monday in lecture, we actually got to this, the Arrhenius equation. We're going to actually take this Arrhenius equation, which is basically, to me, unpacks your rate law constant. Your rate law constant K is equal to, and again, I told you this K0 sometimes will be A, or A0, or A star, okay? That's the Arrhenius constant, picks up the orientation part of the rate. Okay? So it's the orientation factor, K0, times E raised to the negative EA over RT, where EA is that energy barrier. R is the ideal gas law constant, and T is the temperature at which this reaction is occurring in the Kelvin scale. Well, one of the little tricks, and I brought my sheet here, the law of logs. One little trick I told you about is that if you are after an exponent, you can take the log of both sides. It can be natural log like this, or it can be log base 10 or log base anything. The reason we're going to do this is we're trying to get to the exponent negative EA over RT. The next little thing I'm going to do is, remember, if you have the natural log of a product, which this is the product, this is K0 times E raised to the negative EA over RT, we can break that out into the sum of the individual logs. That's exactly what I'm doing here. The sum of the individual logs. I'm doing all of this so I can get to that exponent. We're going to actually do this when we deal with acids and bases too, pH scale. All right, so I'm going to rewrite that. Okay, I'm going to take that last term because that has my negative EA over RT. I'm going to move that to my second term. I'm going to go ahead and bring this exponent now as times. So all I did was I moved this right here and I took this exponent and made it. Okay, so it's all legit. The law of logs allow you to do this. Let's see. Oh, wait a minute. No, this is a different rule. Oh, okay. This rule is, let's see. I don't see it on here. We're actually doing the natural log of e raised to a power is that power. Sorry, this is a different rule. Okay, so the natural log of e raised to a power is that power. Final answer. So we're getting ready to come up with an Arrhenius plot. So this is the Arrhenius equation. The Arrhenius plot now looks like this. Where along the y-axis, we're going to take the natural log of the rate law constant, ln of k. And then along the x-axis, we're going to take 1 over the absolute temperature. And our slope will be negative, and our line will have a negative slope, and the slope will be equal to negative EA over R. That's it. That's your Clausius Clapeyron. That is your Arrhenius plot. Okay? So again, we run it at a couple different temperatures, come up with different Ks, and this is actually what you guys are going to do in lab tomorrow. You're going to run the same experiment you ran last Thursday. You're going to come up with the K value, and you're going to plot the natural log of K versus the inverse of the temperature. Okay. So let's look at an example. This actually is where you have 2 reactants. The overall reaction order is 2. Okay. And we came up with a K at different temperatures, just like what you're going to do. And we're going to use that then to come up with the Arrhenius plot, and from the slope of that, we're going to knock out the EA, the activation energy. Because M is equal to negative EA over R. R is a constant, right? So you're there. And this example looks like this. So here's our various temperatures and the rate law constants. Okay. How does the rate law constant change as the temperature increases?
It gets slower.
Actually, it gets bigger. Yep, it keeps getting bigger and bigger. Yep. And what you're seeing actually is an influence of this temperature increasing to make your K bigger. Which is the other day I was like, oh my gosh, it's in like the denominator of an exponent, but it's raised to the negative power. So, I know. Okay, 50 degrees Celsius. Now, here in a minute when we crunch this data, does this make sense? We're going to have to take the Celsius temperature, get it to Kelvin, and then take the inverse. That's going to be along the x-axis. We're going to take the natural log of this along the y-axis. Yep, that's it. So on for your sheet, your equation sheet for a week from tomorrow, is your Unit 2 exam. On your equation sheet, you will have the Arrhenius equation, but you won't have what an Arrhenius plot looks like. And I've heard some students do this, like right away when you get your stuff, if you want to go ahead and write a little picture of what the plot looks like, that's probably what I would do, or somewhere along the line. All right, let's see what this data looks like then. So this would be your Logger Pro. This is your raw data, the temperature in Celsius and the rate law constants. So this is adding 273 to your temperature. And this is taking the inverse of your absolute temperature, getting it ready for the x-axis. And this is taking the natural log of your rate law constants. So ready to take those last 2 columns and plot them. And this is what they look like. Nice, pretty straight line. Good correlation coefficient. So your slope is negative 1.08 times 10 to the fourth. Let's see. And your slope should be units of whatever your K is going to be per inverse temperature. So since it's overall second order, our units of K are going to have to be liters per mole time. Yep. And so that's actually what you see. And Logger Pro wouldn't know that. I think that had to been manually put in, I think. All right, so let's take that slope and use this relationship, Arrhenius equation, Arrhenius plot, to knock out the activation energy. So for our Arrhenius plot, activation, the slope is equal to negative EA over R. Rearranging that then, the activation energy, which is what we're after, is equal to negative slope times R. And I'll give you M. I will give you the value that of I'll give you the value of R. So the slope we got from the plot is negative 1.1 times 10 to the fourth. So maybe I was wrong with the slope of units, inverse temperature. Inverse of inverse temperature, which is the temperature. Anyway, there's the slope. And the R we use is 8.31 times 10 to the negative third. Units are kilojoules per mole Kelvin. Kelvins cancel. We have units of kilojoules per mole, which is awesome. 2 sig figs. Your activation energy is 91 kilojoules per mole. What a nice, pretty number. And all activation energies will be endothermic, so they'll all be positive. All right. So instead of a set of, was there 5 temperatures that maybe that we had for this, the example we just ran, it's possible, this is a different example, that you actually just have it run at 2 different temperatures. We'll kind of see what that looks like. And my advice is to go ahead and think of your Arrhenius plot and think of 2 temperatures. Okay. This is temperature, or this is, we'll just call this plot 2. This is plot 1. And think of what you need to get the slope to knock out the activation energy. So the 2 temperatures here was a whopping 377 Celsius and 427 degrees Celsius. And you can see the corresponding rate law constants. So with those ordered pairs, we can basically do the same thing we did with Logger Pro and 6 points before. This one, 2.39 times 10 to the minus 7.
Okay.
Liters per mole per second. So up here in this little pink box is kind of the raw data again, a little bit of manipulation there. The temperatures need to be converted to absolute temperature, so you can kind of see where we need to add 273 to both temperatures. That gives you 650 Kelvin for the first temperature and 700 Kelvin for the second temperature, known to 3 sig figs, or known out to the nearest ones of a unit. And then I just brought in the rate law constants that we were given. Haven't done anything there. Sometimes in a problem like this, I would kind of like make it, like it was in Logger Pro, like make 2 lines and make columns. So if we think of what a slope is always, change in, it's rise over run. So change in y over change in x. we kind of scale that to the specific plot that we're looking at. Change in y would be the natural log of k2 minus the natural log of k1. And in the bottom, we'd have 1 minus t2 minus, 1 over t2 minus 1 over t1. I can't remember what my notes do. I think I do one more thing. In my law of logs, I said if you have, like we have in the numerator, we have the log of something minus the log of something. Actually, we could combine those together and say it's the log of the ratio, the log of k2 over k1. I think that's what I do in the next slide. All right. So at this point, I just plug in, okay? And I'm not sure if I were doing this problem, this is the way I would do it, but it worked well on my slides. So in the numerator, we have the natural log of the ratio of k2 to k1. So the natural log quantity 2.39 times 10 to the minus 7th over 2.15 times 10 to the minus 8th. There's your k2 and k1. In the denominator, we have the inverse of T2, which is 1 over 700 Kelvin, minus the inverse of T1, which is 1 over 650 Kelvin. Looks like a beastie thing to plug in your calculator. Can't remember what my builds are, but here we go. So with my builds, you can see I evaluated the numerator, I evaluated the denominator separately. And then when you divide that out, you get a slope of 2.2 times 10 to the 4th Kelvin. I think I'm going to backtrack. Units of slope will be inverse temperature. I said it would be K inverse temperature, but units are 1 over Kelvin. Final answer. Nope, final answer. They're Kelvin, because over here we have 1 over Kelvin, which is the
So
denominator.
the units of slope won't be units of Kelvin over 1?
Yeah, yes. Final answer.
So it'll just be units of Kelvin.
Units of Kelvin, perfect, that is true. Because, yes. I'm still thinking about astronomy, I think is what it is. So now, don't let this kick you in the butt. M is equal to negative EA over R. So solving for EA, right? EA is equal to negative MR. And we're after EA. So we're going to go ahead, in this case, take a negative 1 times negative 2.2 times 10 to the minus 4th Kelvin, that's our slope, times the value of R we need to use here, which is that 0.00831 kilojoules per mole Kelvin. And our units of Kelvin cancel, we're left with kilojoules per mole, which is great for activation energies. We round to 2 sig figs, and this is what I got. I got 180 kilojoules per mole. Think of activation energies. Think of them on the diagram. It's a barrier. It's an energy barrier.
That, the R is constant. That
Yes.
we'll be given that, right?
Yes.
Okay.
Yes.
The units don't change on it, right? Or is
What?
it- The units don't change on it like they do, like they did on the other one?
Right. And when the units changed, it was actually a different value for R. So the one you use in PV equals nRT has different units. Different units and a different number. All right, very good. So we're going to use Logger Pro. Take a quick look at these. I didn't look at these in advance. That's always dangerous, or should I say fun. $14.51. There we go. Okay, so rate constants are given at a couple temperatures here, and you're supposed to come up with the activation energy. And so this is like the one that we just did, right? And you can see you can, work it just like we did in your notes. But you can see, like I kind of told you here, I would kind of think of it like a table, kind of coming up with the different columns. It's the same diff. All right, so for this one, so this one you have to use Logger Pro. And actually doing this one will help you, and it's in case you don't have the answer to it, but doing this one will help you with your lab. This is what you guys are going to do in lab. All right. And then the next one looks like this. It's, let's see. This one, don't do 56 yet. Don't worry about 56. 56 will make more sense when we talk. This is part 5. Don't do 56 because this question will make more sense after we do parts 3 and 4.
So
Okay.
we'll get assigned later.
Maybe, if I remember. So it might be. How's that for being committal? Okay. All right. All right. Back to part 3. It's all good. So clear back in part 1 or part 2, how did I say you get your reaction orders? Do you remember? How do you get these guys?
Experimental data.
Thank you, experimental data, that's it, exactly. And, let's see, how do I say this? So you guys did it experimentally by changing the molar concentration of your reactants and looking at the effect on rate, right? Okay, now, in that time, how do I say that? I'm switching gears now. We're still going to do it experimentally, but we're just going to do one experiment. I think this is right. Yeah. We're going to do one experiment, and we're going to check the rates in that one experiment. Okay, one experiment, and we're going to check the reaction rates over time. Okay? Or the molar concentration change. So this is, that one experiment is called time concentration. So I said check the reaction rates, but basically you're going to have run it once, and you'll have time, and you'll have the diminishing concentration of your reactant over time. I'm going to show you how you can use that to get to what the reaction order is. Okay? So it's called time concentration data. So, yeah. So we know that the concentration of your reactant is going to go down over time, right? And how it goes down is a function of its reaction order. So it will tell the story. So we're actually going to focus on 0 order, 1st order, and 2nd order. And there's going to be a graph for each of these. It's kind of fun. I think, like I've told you before, when I tell my kids at home it's going to be fun, they just roll their eyes. That can't be good. Okay? So we're going to focus on 1st, 2nd, and 0 order. Not only will we be able to tell what these are, 0, 1st, or 2nd, but from the graph, it's wonderful. We're going to be able to knock out K. It's just wonderful. Again, just running it once, time, concentration of the reactant. So I'm going to kind of go over here. Let's start with 0 order. 0 order are just kind of creepy. That's where, remember, if we put that as 0, this term goes to 1, and this term does not show up in my rate law expression, right? So that means that the reaction rate is independent of the molar concentration, which is kind of fun if it's 0 order. So if it's 0 order, then your rate law constant, well, your rate law constant is constant. If it's 0 order, then your rate is constant. And I was like, I actually posted something today because on the Twitter feed, our Twitter feed, and it looks like this. And I don't mean to throw you off, but if you're like me, you're like, now how does that look? And I probably will erase this. But if we were looking at our reaction rate and it's zero order, and this is time, okay, our reaction rate over time is constant. Okay, now that doesn't mean that the molar concentration of your reactant, of course, it's going to go down. Small question. You know, it will go down. But anyway, that is so cool. Okay. Well, a little bit of calculus. It's been a while since I've done calculus. But calculus is great at handling the changes in. It's great at handling slopes. With a little bit of calculus, actually, we can go from rate is equal to negative change in molar concentration of A over time, which is equal to K. We can integrate that and come up with, for zero order, and now this is something that I am going to write on the board. For zero order, we have this relationship between the molar concentration of our reactant, A, the initial molar concentration of our reactant, A sub 0, the time, T, and K, the rate law constant. So this is zero order. I'm thinking of Z Nation. I thought it was pretty. Okay. This is for zero order. And you will see that equation on your test on Thursday, but you have to recognize it as being zero order. Okay? This is what we call the integrated time concentration equation for zero order. Okay. Well, I mentioned plots, so how are we going to plot that? Well, we can rearrange it a little bit, I think. Oh, I should have added this. So A0 is the initial molar concentration of A. A is that changing molar concentration of A over at a particular time T. And K is your rate law constant. Okay, so we can take this and rearrange it a little bit to get something we can plot. I don't know if I necessarily, I'll do that. So A is equal to plus KT minus KT. Okay, so then we are ready to have something we can plot. If we plot along the y-axis the molar concentration of A, and along the x-axis time, okay, we will get a negative slope. Okay, if it's zero order, it's going to be a nice straight line. Only if it's zero order will this plot give you a straight line. And the slope will be equal to M. The slope of this is equal to negative K. It's wonderful. That's all zero order. And all I did was kind of the proof, okay, of how we get that. Let's just say for kicks, you plot the molar concentration of the reactant over time, and it's not a straight line, then it's not zero order. That's it. All right, cool. Oh, we've been talking about kind of the y-intercept. So the y-intercept is, that's kind of fun, and it makes sense because it's time zero. Actually, the y-intercept is your initial molar concentration. Okay, so I'm going to draw a line, and I'm going to change from, we're going to do a similar kind of proof, change it up, and we're going to make it first order. Okay, so for first order, our rate law expression would look like this, where we have the molar concentration of A raised to the first power. So rate is equal to K times A raised to the first power. Well, rate then is equal to negative change in A over change in time. Go ahead and do a bit of calculus, integrate it, and we come up with this relationship. So now we have the natural log of the ratio of the molar concentration of A at time t divided by the initial molar concentration of A is equal to negative KT. And you'll see that one on your equation sheet Thursday also. But you have to recognize that it's for first order. So we kind of talked a minute ago about taking the differences of the, this is for the Arrhenius plot, the differences of the K's and putting them into ratio. We can do the other too. We can separate those back out into the ln of A minus the ln of A0. Okay? And when we do that and kind of move the ln of A0 over to the other side, of course now it's positive, and we end up with this kind of relationship. So this is also true, just kind of looking at it different, and I have one more way to look at it, I think. This is actually finally something we can plot. The natural log of A at time t is equal to negative KT plus the natural log of the initial molar concentration of A. Line up y is equal to, yeah. That's actually the thing that we can plot. If we put y is equal to mx plus b, then we have our next plot, and it looks like this. Along the y-axis now is going to be the natural log of A, and along the x-axis it's going to be time again. And we should again have a negative slope, and the slope of the line will be equal to negative k. This time the y-intercept is equal to the natural log of the initial molar concentration. So we, in this case, if we take the natural log of the molar concentration of A and we plot it against time, and if it's a straight line, then it's first order with regard to A. And sometimes students might say, well, what defines straight line? Like, is it a little bit of a curve to it? No, it's got to be straight. Okay. If it's not straight, then it's not first order. And then last but not least, we have this one. Oh. This is an example of the hydrogen peroxide decomposing over time. It's first order, and this is actually a good test to kind of show you that the natural log of the molar concentration as it decayed versus time showed us a straight line showing the first order test.
So, if there's multiple reactants, would you have to do a test for each reactant in, you know what I mean?
Yes.
Okay.
Yep. Yep. And that's a good point. A lot of these, I guess all general chemistry books would do this, but Petrucci does, and what I do is just look at a lot of decomposition reactions where there's only one reactant. So it's I kind of went about that way.
But once
you should be able
once
to.
you found one, you could use the log to find the order of the other, right? If you have the reaction time.
If you found the reaction order of one, then it kind of opens up the door to finding the other one. Is that what you mean?
Yeah.
Yeah.
Because if you know the K value in the reaction order of one of them is to reactant reaction, you could use that to find the order of the second one, right? Kind of like what
I
we did
think so.
yesterday,
I think so.
algebraically.
I think so.
Okay.
I think so, but I think you're right in that if you had two things that decayed over time, you could track them separately and do a change in the molar concentration over time and see which fit linear. Was it straight molar concentration, the natural log? The last one I'm going to do for this test is an inverse of the molar concentration.
Okay.
So, yeah. Yep. I think so, Mike. So for the second order, looks like this. So if it's second order, we would write the rate law expression as the molar concentration raised to the second power, excuse me. We go ahead and do our integration, and it looks like this. Okay, so these equations that I've been kind of telling you that you're going to have on your test as an equation sheet are called the integrated time concentration equations for 0, first, and second. And actually, in Friday's lecture, we're going to see how we can use those to work problems if we know the reaction order. So here we have for second order, the inverse of the molar concentration of, I'll just do the bottom one. Inverse of the molar concentration of A at some time t is equal to, in this case, a positive kT plus the inverse of the initial molar concentration of A. So that one there at the bottom is ready to go ahead and plot. So if we go ahead underneath there and kind of superimpose our y is equal to mx plus b, you can see what our plot is going to look like. So our plot is going to look like the inverse of the molar concentration of A, and again, time along the x-axis. In this case, we're going to have a positive slope, and our y-intercept is actually going to be the inverse of the initial molar concentration of A, which makes sense. And your slope then is going to be equal to k. So here slope is positive, and you just pick k off of there. So like all of these said, if you run any test, if we ran all three of these tests and nothing was linear, then you're like, oh, I guess it's not 0, first, or second order. Okay. Makes sense. They're kind of fun. I like the topic that we're going to do on Friday, too. I think that's kind of fun. Okay. So let's see what an example would look like. And to me, this is, once you have your time concentration data, if you have Logger Pro or some sort of spreadsheet, you're so close to being able to knock out all three of these, really. You just have to add a calculated column and make the graphs. It's really not too bad. So here's the time concentration data for the decomposition. Is this a decomposition? Yep. Nitrogen dioxide. So that's our raw data. So this is kind of like what the homework's going to be like. Basically, we're going to take that data and we're going to make 3 plots. We're going to see which one's straight. Bottom line. And then whichever one is straight, we're going to pick off the k. Okay. So if it's 0 or first order, it's going to be negative k. The slope is equal to neg k. And if it's second order, the slope is equal to k. Don't even have to throw in the negative there. Oh, see, this is kind of what you were asking, Mike. Says how this method can be used for reactions involving 2 or more reactants. I'll cover this later. What do my slides do then?
Let's see. They went from there.
Okay. Pull that. Aw. Well, I haven't something. So this isn't what your slides do, is it?
Yeah, that's what ours do.
Is that what yours do?
Yep.
Yeah, it's not like right away, but it's there.
Because I was looking for the example. Mine doesn't have the. Oh, here it is. Okay. Gotcha. This is what I wanted to cover right now. Well, why don't I'll cover, I think we've done well. So we'll just go ahead and call it a day. And I'm going to, thanks for your patience. So I did find where my missing slides, I had hidden them. So we'll finish that example and I guess kind of take a look at the 2 reactants. And then knock out the next part, which is part 4, on Friday. Very good.